In this section, we want to start moving away from our conversation of derivatives and start talking about a new topic, which is integration or integrals. Though we'll see pretty quickly, derivatives are going to pop back up in a very connected way to this new topic. First, we want to look at the idea of estimating the area under a curve. What we have graphed here is a function f of x is equal to 2, and we're told we want to find the area of this curve, the area under this curve between x equals 0 and x equals 4. So we can draw in a couple of boundary lines, one at x equals 0, one at x equals 4, and we can highlight the region that we're trying to calculate the area of, which is the area bounded between this curve and the x-axis. In this case, this is a pretty simple calculation, doesn't require any calculus, because this region is rectangular. And we know, based off the information that we're given, that this rectangle has a width of 4 units and a height of 2 units. So the area of that rectangular region would just be 2 times 4, or 8. Translating that into some calculus-based information, we would draw this elongated S symbol, which is the integral symbol. We would say the integral of f of x dx, where dx is telling us the variable that we're integrating with respect to, evaluated from x equals 0 to x equals 4, will be equal to 8. We refer to this expression as the definite integral of this function f of x evaluated from 0 to 4. We translated that into some calculus-based notation, but again, that problem didn't really require any calculus at all. It was a simple geometry formula that we've probably learned ages and ages ago. But now we want to take that same idea and expand it to something that doesn't fit one of our traditional geometry formulas or one of our basic geometry formulas. Now what we have is a function g of x equal to x squared. We still want to find the area below this curve, so the area between the curve and the x-axis, between x equals 0 and x equals 4. Meaning we're trying to find the area of this shaded region. The graph of x squared isn't a straight line, so this doesn't create a triangular region. And really, again, it doesn't fit anything that follows one of our basic geometry formulas. So now what we want to do is calculate that area under the curve, which is the integral of g of x dx evaluated from x equals 0 to x equals 4. Over our next several topics, we will build up to the point that we can evaluate that integral directly, that definite integral. But for now, we're just going to look at creating approximations. What worked really well in example 1 was drawing a rectangular region. So we could consider doing something like that. But if we do this, we see that we get a lot of excess area. For instance, we'd be calculating this entire area, which is not part of the region that we actually want. So that method's not going to work incredibly well for us. But what we could do is, rather than drawing one giant rectangular region for the entire area, is we could break this up into smaller rectangular chunks. So we could start off, I'm going to start off on the far right end, and I'm going to draw a rectangle up until I hit this function value. Then I'm going to make this rectangle 1 unit wide, and then drop it down. Then I'll do the same thing at x equals 3. I'll draw up until I hit that function, and then create this rectangular region. And I'll repeat that process all the way down until we hit x equals 0. Now we've created 4 rectangular regions, which give us an approximation for this area. We can see that we still have some additional area that we don't want to calculate, but we have an approximation that's a lot better than just that one large rectangular region. We can find the area of each of these rectangles by looking at their height and width. In this case, since we started at x equals 4, this rectangle would have a height of 16 and has a width of 1 unit. The next rectangle has a width of 1 again, and since we drew that line up at x equals 3, it has a height of 9 units. Since we drew this line up at 2, this would have a height of 4 units, and this one would have a height of 1 unit. So we can find each of the areas of those rectangular regions by taking 1 times 1 plus 4 times 1 plus 9 times 1 plus 16 times 1, and we get an area of 30 units, 30 square units. Alternatively, this is going to start to get a little sloppy as I write over myself. We could draw rectangular regions from the left endpoint of each of these intervals. So I could start at 0, 0, and go up till I hit my function, which is at 0. So I draw a rectangular region straight across that has a height of 0. I could draw up until I hit my function value and then cut across. Draw up until I hit my function value and cut across. Draw up until I hit my function value and cut across. So now I have 4 new rectangular regions, which also have a problem. In this case, we're missing some of the area that we want to calculate. But we could calculate the area of each of those rectangular regions, which would have a height of, or an area of 0 times 1, 1 times 1, 4 times 1, and 9 times 1, since we were using the left end of each of those endpoints. So that would give us 0 plus 1 plus 4 plus 9, or an area of 14 square units. So we can look at these approximations, drawing these rectangular regions using either the left or the right endpoint of each interval. Obviously, they're approximations. There are going to be areas that we're missing. But the idea that we can draw these rectangular regions to find these approximations is a step towards the goal of what we want to do, which is finding this exact area, the exact result of this definite integral, which we're not talking about how to calculate now. But later we'll find out that we could calculate this as exactly 64 thirds, or approximately 21.33, just to see the difference between our approximations and that exact area.